last time we were actually very quickly talking about the stellar population synthesis, which lets us calculate the properties of galaxies by observing their spectra. It's a very powerful technique, and it involves like stellar evolution, initial mass function, dust absorption. A lot of these very important processes put together can give you a final spectrum that you observe. So anyway, we are not going to go into details of this, but this is very important, is all what I'm going to say. Like, for example, a lot of this work on JWST and so on, inferring the age of the stellar population, whether there is dust or not, comes from this kind of work. Okay? So whenever you have galaxy spectra, you need this stellar population synthesis to interpret those spectra in terms of physical properties, like star formation rate, star formation history, and things like that. Okay. So I'm actually running a little late according to what I want to cover, but I sort of thought I just sort of cover very basic stuff anyway. So for example, I had mentioned already about these bands, U, B, V, R, I band. So that people observe in, this is the transmission of the sky. If you're observing from the ground, these are good places to observe. This is a bad wavelength to observe. This is really bad also. And these just depend on water absorption by water vapor and things like that. We have the atmosphere, and you see these bands actually are coinciding with this because you can only observe in those regions. So typically you observe only in a narrow band or 2 or 3 bands. So you have a very limited information. For example, for a spectrum of a star, which is shown here in the background, this is sort of a star which is more massive than the sun, because see, the peak is leftward of 6,000. I mean, it's sort of in close to UV. Okay, so I think it's a star or something like that. So basically, if you see this portion only and not the resolved spectrum, but the amount of light that you get in this filter, how do you get how do you infer properties like this stellar type and things like that? So this is people face all the time. So this is flux measured through the band pass. That is, if you measure in one of these bands, what is the observed flux? This is the transmission of that band pass and the true flux as a function of wavelength, and then sum it over, sort of a natural thing. So this is not an attendance. If you're attending for the first time, you put your names here so that I can add you to teams. Okay, I won't really be taking attendance. Okay, so what you measure is, say, in V band, some absolute or apparent magnitude, but what you're interested is in the total luminosity, and this correction is called a bolometric correction. So these are terms that when you encounter the first time, you should not just be totally zapped. These are not, I mean, you can understand them in more intuitive things. So bolometric correction basically tells you that you're only observing in a narrow band, but the source is emitting across wave bands which you're not measuring. So depending on the type of a star, for example, you can calculate the bolometric correction. For example, if you're measuring this star in R band, the bolometric correction will be large because its flux peaks at this wavelength, right? In the same way, so this BC. So okay, tell me about this. Whether bolometric correction for a star will depend on the stellar type. Yes or no? Yes, right? Because if you have a star which is peaking in B band, you don't lose so much flux. So bolometric correction depends on the source that you're observing. Okay. The other thing that we have to be careful about when you're observing, in fact, you're having that instrumentation, those instrumentation class lectures, and I'm sure some of this will be actually covered or was already covered. Right? This astronomical techniques course, right? In that, some of this definitely was covered. The other thing that you have to be careful about is the night sky is not totally transparent. In fact, it emits. So if you look at the optical window here, and if you just look at sky emission, there are these lines, right? So there are molecular oxygen bands, and there are neutral oxygen atom lines, and so on. So if you're measuring spectra of a background source, they can get contaminated by this. So you don't want to observe. Normally observatories are located at mountain tops and deserts and things like that, and that's because of and away from the northern poles. Away from the poles. Why would you think that you want the observatory not so north or south?
It covers less of the sky.
Aurorae, right? If you have these aurorae and so on coming up, and they are full of these, the beautiful lights that we see are these. So go to a place where there is no humidity, which is high on top, so that the column of the gas of the atmosphere that you're looking through does not give all these things that you're not interested in. Okay. And of course, space is the best because there's none of this to worry about. So I'm actually giving you like a very quick run through of various things that you should actually be aware of. So what is shown here is in this plot is the abundance of various elements in the sun. Okay. And the abundance is actually characterized in this way: X, Y, and Z. So X is the mass fraction of hydrogen. So take sun. How much mass there is in the sun in form of hydrogen, and divided by total mass. That's X. Similarly, Y you do for helium. Total mass in helium divided by sun's mass, and everything else. So in astronomy, everything except for hydrogen and helium are known as metals. So that Z is the mass of all the other elements divided by the total mass. So this is the definition of XYZ. This is very commonly used across all of astronomy. So it's better to just know what these mean. And these are the values for XYZ for the sun. So the mass fraction in hydrogen for the sun is about 74%. Helium is 25%, and 1 to 2% of metals. Okay, so metals are very sparse, but yet they have huge impact on the star. Why do you think that may be? These are all like, basically they are very good absorbers and emitters. Metals are efficient emitters, and they provide a lot of opacity, especially at specific frequencies where they have absorption and emission lines. Okay, a lot of these Fraunhofer lines from the sun are actually sodium lines, calcium lines. They're all metal lines. They're extremely rare, yet they produce these signatures.
These numbers include the atmosphere
Of the sun? No. So these are photospheric abundances. The way you measure this is look at the absorption lines in the sun. And if you have higher metallicity, you'll have deeper absorption lines. Okay, so it's very sophisticated modeling, but the idea is the following: if you don't have, say, if you don't have calcium, you should not have calcium absorption. If you have more higher fraction of calcium, you'll have a deeper calcium H and K line. So that's sort of at 0th level how you should see it. But in reality, people actually run simulations, produce produce mock spectrum, and then compare with what is observed and tune their different abundances till they get a.
So this is about the interior.
This is photospheric abundance. This is photospheric abundance. This is outside. The interior abundance is extremely difficult to get. Uh, so what you assume is that the photospheric abundance and the interior abundance is more or less the same. And that's sort of not a crazy assumption because the sun does not evolve very quickly. It's only halfway through its lifetime. It's 5 gigayears ago. So this is one of the assumptions that people use. But we can get a sense of interior abundances of the sun by something called helioseismology. You cannot directly sort of see inside the sun, but you can actually understand about the interior of the sun and specifically speed of sound inside the sun by observing solar oscillations. So, there is like a solar model which does all this. In fact, there was discrepancy between some of these models, and there was like as late as 2010, there were like major revision for sun's abundances. Okay, and you see this is mass abundance in the sun, and you see there are patterns here. Stable nuclei are more abundant, unstable nuclei, less stable nuclei are less abundant. So there's a lot of nuclear physics which determines why some elements are more abundant. So hydrogen, helium, and lithium, deuterium were produced in the very early phase of the universe. As soon as nuclei started forming, they sort of combined and formed hydrogen and helium. But all the other metals like carbon, oxygen, and so on, were produced inside massive stars. Okay, the more massive a star is, the higher temperature it has at the centers, and it can burn higher and higher atomic mass nuclei at its core. So this carbon, oxygen, etc., are produced at the centers of stars more massive than the sun, and they have winds. And at the end of stars' life, we have supernovae, and these sort of release these metals into the interstellar medium, right? So, and sort of it pollutes the interstellar medium, and the next generation of stars which form have higher metallicity. Okay, so this is how a lot of this goes. A lot of these alpha elements like magnesium, silicon, and so on are produced in core collapse supernovae. Iron is supposed to come from type 1a supernovae, these thermonuclear supernovae. Type 1a, if you recall, are these standard candles that are used. So anyway, this is like a whirlwind tour of various concepts. And this is one way in which people specify metallicity of a star. So square brackets A by B for a star, say, is defined as number of atoms of A divided by number of atoms of B. So, for example, you want to see Fe by Fe is iron. Iron by hydrogen of the sun of a star relative to the sun would be calculate Fe by hydrogen for that star divided by that of the sun. So if you have this Fe by H of -2, that means this star has 10 to the -2 times less iron compared to the sun. Okay, just to be aware of. Yes.
In the book, it is written that these higher mass elements,
Yes,
they are created in explosive burning of supernova.
the rapid, right? So there are two kinds of right. So iron is the most stable nucleus, right? The binding energy per nucleon is the highest for iron. So anything which is above iron has to be produced by in fast processes, because it's sort of non-equilibrium. Suddenly you create certain conditions and put a lot of energy. You're able to go beyond this sort of iron peak. So there are two kinds of processes, like, so basically, how do you go past iron? The nuclei have to capture neutrons, and those neutrons have to beta decay and make protons, and it increases your Z, the atomic number. And if the number of, I mean, depending on how fast you, uh, how fast the nucleus captures new neutrons relative to the beta decay time, you have S and R processes, slow and rapid processes. So you have nucleosynthesis through S process in AGB events and so on, and also supernovae. And the R process, like this neutron star mergers, give rise to a lot of R process elements. So, these are all details which I'm really not, I'm not prepared to go into, but it's good to know at a course brush level these things. Okay. Now we'll actually come to the structure of the Milky Way. So the Milky Way, of course, are these island, Milky Way is like a typical spiral galaxy, these island universes that we learned about previously. And so the sun is about 8 kiloparsecs away from the center of our galaxy. Our galaxy is a spiral galaxy, a barred spiral galaxy, or of type SBC. We'll actually come to the morphological classification of galaxies later. So this is the sun. This is the galactic center. There is a supermassive black hole in the center of our galaxy. And it's about 4 million solar masses. So lot of dense gas and stars are in form of a disk, and these stars are going around the potential due to, they're going around in form of close to circular orbits, but there are, of course, fluctuations on top of that. There are something called thin and thick disks. So stars in the disk so the older the stars are, they are thicker, they form thicker disk, thicker in spatial extent. And the reason they form a thicker disk is because as the star is orbiting around the Milky Way, it encounters all these irregularities, spiral arms and molecular clouds and things like that. So it gets kicked, random kicks because of these. It's almost like collisions, right? And the longer the star has been around, the more it has been kicked randomly. So that's why its velocity dispersion is higher, and that's what gives it a thicker height. On the other hand, young stars like O stars and so on are just born now out of the gas. Gas is cold and thin, so it is a thinner structure. So thin and thick disks. In addition to the stars, there's a lot of gas in between the stars, and this is the gas out of which stars form and also return their metals after they die as supernovae and through massive stellar winds. Okay, so this is about it. So bulge. So in addition to the disk stars, there is almost a spherical distribution of centrally concentrated stars. These are old stars. And this distribution, this sort of collection of stars at the center is called the bulge. In addition to the bulge, there's also very diffuse distribution of spherical distribution of stars, which is called halo. Okay, so bulge is very centrally concentrated old stars. Halo is extremely difficult to perceive because it's so diffuse. Okay, so I'm just telling you all the components. It's just good to know. These things we have already encountered in the Shapley-Curtis debate, that these are globular clusters which are symmetric around the galactic center. So globular clusters are much more extended as well, tens of kpc, up to 50, 100 kpc. And all this is embedded in a dark matter halo, right? So we'll actually come to that. So if you try to measure the velocities of these objects here, they appear to be moving fast compared to how much mass you would think there is just by seeing light from all these different components. So this is the dark matter problem. We'll actually come to this. And this, there are different populations of stars as well. There is population 3 stars, like the earliest stars, the first stars, which are supposed to be very massive and luminous and low metallicity, because in the early phases of the universe, there was much less pollution. You need stars to pollute. All metals are produced in stars. Okay, so if you have first stars, there has no. It's all hydrogen, helium, from which it starts. So Sun is like a population 2 star. So after population 3 produces metals, cooks metals in their cores, they put out galactic winds, pollute it, and out of that metal enriched ISM, you form the next generation stars. Yes, Prameet.
Sun is like a thick disk or thin disk?
It's a good question, actually. Sun is actually pretty close to the center. So I would guess it's part of the thin disk, So it's a continuum, actually. The older the stars are, the larger their vertical dispersion is. So it's not like, oh, there's only two like very clear disks. It's a continuum. The older stars are very likely to be, have large vertical velocity dispersion and hence a thicker scale height, right? Okay. So in any case, none of these things, like, this is just schematic, and this should not be taken literally. Okay. Okay. Right. So as I mentioned, the star, there is a lot of gas between stars, and that gas is called the interstellar medium. So this is a schematic of, the disk. If you zoom in a little bit, the disk part, and see an edge-on view, this is how it looks like. This is the galactic center. You can actually see this sort of a bulge distribution. Some galaxies have much more prominent bulge, others not so much. This is the sun, 8 kpc, 8.5 kpc away. This is the scale height of stars around the sun. So scale height means if you go at that height, the density of stars drops by a factor, factor of 2, say, okay, or factor of E, right? Right. So this is, and all these stars at the center, there is a lot of gas, which is known as the interstellar medium. And this sort of roughly gives you the budget of flow of mass from one component to the other. Like, ISM, interstellar medium, and stars are not like, they're not totally segregated systems. Gas from the ISM forms new stars. After the death of stars, metals, which is sort of gaseous form, is released back into the ISM. So it's very dynamic. So this is actually the flow of mass on the right. So, the ISM receives mass from this diffuse baryonic halo, which you cannot see here. And that mass comes into the ISM, cools into the ISM. This is the mass of the ISM, like about 10 to the 10 solar masses. This is the star formation. So ISM, you get about a half solar mass a year. In fact, more than what it receives, it sort of gets, at least here in this cartoon, goes into star formation. and a little bit is returned through galactic, through supernova outflows and massive outflows. So 0.5, and so 0.8 net goes out. So that what it means is if this situation continues for long, the ISM will be exhausted. This is just a very schematic thing. So ISM is an extremely dynamic thing. If you look at cosmological timescales, the interstellar mass can actually grow and shrink by a huge amount. So this is the stars, and stars much less massive than the sun don't quite evolve. They're sort of sitting on the main sequence, but more massive stars evolve off the main sequence and give rise to compact objects like white dwarfs and neutron stars and black holes. Okay, so the age of an O star is like 5 million years. 5 million years is a very, very short time on galactic timescales. Like, it takes 200 million years for the sun to go around Milky Way at its location. So 5 million years is nothing. It just moves a little bit. If a O star is born, it will just go around a little bit and then just die, unlike the sun, which has gone around the galactic center for tens of times. Okay. So yeah, this is the flow of mass. Mass is not the only quantity that stars produce. They also produce a lot of energy, right? So stars are, self-gravitating objects. That's why they don't collapse, because gravity is not able to crush it totally, because the pressure forces and because of nuclear burning at the center, it produces energy. So have you heard of Kelvin-Helmholtz contraction? Oh, yes. So even as long ago as like 100 years ago, people didn't know what powers the sun, right? And in fact, Lord Kelvin, for whom we have the Kelvin temperature scale, thought, and a lot of the contemporaries thought that it was gravitationally powered. That is, you have this ball of this hot ball, it loses energy, and as it loses energy, it sort of shrinks, and that's called Kelvin-Helmholtz contraction. But if you put in the numbers, right, that is, you calculate the gravitational energy of a sphere, which is just gm squared by r times the factor, right? 3 by 5 gm squared by r is the minus is the gravitational energy of a constant density sphere, right? And if you divide it by the luminosity, you get a time scale. Luminosity is, so that time scale is very, very short. It's like 10 million years or maybe 100 million years. So biologists and geologists say that the Earth itself is longer than a billion years. How can you say that the sun is only is less than a giga year? So there have been things back and forth. So a lot of science develops by looking across their own discipline. So then people figured out we need something else to power the sun. Anyway. Yeah, so I hope everyone knows about that. If you don't, please read up Kelvin-Helmholtz contraction. So this is nuclear power produced at the center of the stars. Since the center is so hot, it produces a lot of light. Hot things produce light. These stars, these photons at the center diffuse out of the star. This light, this UV and optical light, interacts with the interstellar medium. There are atoms and molecules in the interstellar medium. They can ionize the interstellar medium. They can, like if you have UV or X-ray photons, they can do photoelectric effect. Like they can kick out electrons and energize the interstellar medium. Interstellar medium is also an extremely complicated component. It's gaseous, but it also has magnetic fields and relativistic particles called cosmic rays, and extragalactic photon. There's also light, which is there in the ISM all the time, right? The CMB and the light coming from the stars, which is called interstellar radiation field, right? And interstellar medium consisting of these atoms, which are sort of heated and excited by radiation, can also cool down and lose its energy. For example, right, I mentioned that in the starburst galaxies, most of the radiation does not come directly out from stars, but it's absorbed by the dust, which gets heated up and emits far infrared radiation. So the big thing which is missing here is the dust. Dust, even though it's 1% by mass of the ISM, it's an extremely important component of the ISM because it regulates its thermodynamics. It gives rise to a lot of chemistry in the ISM. The way molecular hydrogen forms from atomic hydrogen in the ISM is through dust. Dust provides a catalytic surface on which the reaction of hydrogen combining with another hydrogen, giving rise to molecular hydrogen happens. So dust is extremely important. Yeah. So magnetic fields. The interstellar medium has magnetic fields because it's ionized. A lot of it is ionized, and ionized gases or plasmas can carry current, and current gives rise to magnetic field, right? Del cross B equals mu naught J. So if you have J, you will cause B. So the interstellar medium has, the typical value for interstellar medium magnetic field is microgauss. Magnetic energy, B squared by 2 mu naught. Yeah, that's right. So you don't have electric fields in conductors. A lot of this is plasma conducting. So electric field is essentially zero. That's why you have magnetic energy, but it is electromagnetic energy. This one, yeah, these are all uncertain. So take it like within a factor of 2 or few. Good question. It's actually coming from farther out, so it is somewhat lower metallicity because the things which are near the stars have been polluted the most. In fact, it's the IGM, intergalactic medium, from where eventually this stuff has to come in. Okay. That's correct. But supernova explosions happen inside this disk, right? So it's sort of like if you go to the factory area, that's where you'll have more pollution. If you go further out, you'll have less pollution. Okay, so this is the CMB. We have already seen it. So these are the tiny fluctuations that you have heard so much about. This is actually also a CMB image. Can someone tell me why does this look so different from this? This is also a CMB map. Why does this look different from this?
That is basically because of Doppler shift.
That's right. That's correct. So we are not at rest relative to the CMB. We are moving in some direction. This is the dipole anisotropy due to our motion towards some point. Okay, it's about like 300 kilometers. So these are the tiny fluctuations. Look how much the universe has changed. Here, there are no fluctuations. It's perfectly uniform initial conditions, so to speak. But now we have all these galaxies, planets, stars, and all that. So all that actually arises from these tiny fluctuations. You will learn about this in your GR and cosmology course. But for us, why is it important? And you will also learn in that course why the fluctuations are there and why are they needed. In fact, they are needed to form galaxies. If you don't have fluctuations, you don't form galaxies. Okay, simple as that. So this is your CMB map. These tiny fluctuations seeded something called gravitational instability. Right? If you imagine a uniformly spread matter. And if you sort of accumulate matter somewhere, make it over dense at some region, its local gravity is stronger than its neighbors, so it pulls more matter, becomes more gravitating, and so on. So if you have a uniform ideal gas, for example, and if you bunch it up and leave it, it's stable, it just gives rise to sound waves. If you take normal gas, non-self-gravitating gas, and just perturb it, it's stable, it just gives rise to sound waves. On the other hand, if you take gas which has gravity, which has self-gravity, and which is cold enough, it can become gravitationally unstable. And this is called Jeans instability. So what we believe is that all these fluctuations underwent gravitational instability in this expanding universe and gave rise to what we see here in form of galaxy distribution. What is shown here is actual data of the distribution of galaxies, as measured from surveys. And you see, wherever you have a blue point, that's one galaxy. So you have millions of galaxies and just put points for all the galaxies. Of course, you cannot see the dimmest of the galaxies. That's why as you go to, so the x-axis here, the radial axis here is the redshift, which is sort of distance. The farther the things are, you will only be able to see most luminous galaxies, right? Because the flux is small. But the thing to notice is that the distribution of galaxies is not uniform. There are sheets and voids and filaments. It's very filamentary. Okay, so this is called large-scale structure of the universe. And this is caused by gravitational instability. Okay, so waves and instabilities are like two aspects of the same coin. Right? A dynamical system can be stable, like the sound waves are a stable response, or it can be unstable, like this inverted pendulum. So gravitational instability is like an instability. If you start with tiny perturbations, these perturbations grow. Yes.
Other scale, like the light assumption.
Oh yeah. This is basically, you just look at some angle, look at this angle in the sky. Okay, so you just choose one slice, a constant RA deck or something, anything, and then just put all the galaxies in that. In fact, this should be like in principle, you have two angles, so this should really be like you should go in there and see. It's a three-dimensional. You can actually experience this in a 3D. The actual thing is not this, but it does. It's like a slice of that 3D distribution, which you can appreciate. Okay. So this is, again, I'm not going to talk too much about this, but this is our current understanding of the contents of our universe. Most of the matter that we know and love is tiny, only 5%. And we're all, this is where standard model applies, and this is where what we know. There is dark matter, which holds the galaxies together. We don't know what its sort of fundamental constitution is, and we don't even know whether our interpretation of these large velocities is correct, whether it is actually some particle or is it something else, or the gravity changes at these scales. And then there is this accelerated expansion of the universe, which we encounter a little bit dark matter. I mean, how do we know about dark energy? We know about dark energy precisely by doing what Hubble did, right? You just put, you measure the velocity of a galaxy and you measure its distance and put them X versus Y and see how does this look like, right? So Hubble and people were, they were looking at very nearby galaxies. So, if you have a if you have a distance versus velocity diagram, if you only look at nearby galaxies, you just measure the local slope. But the actual evolution of the scale of the universe and the age of the universe can be more complicated, right? For a short time, you can assume the trajectory to have constant velocity. I'm actually not going to go in details of how you interpret it because this is not a cosmology course, but I mean, the main observational thing is that the type 1a supernovae appear fainter than what you expect, okay, from their present velocity. What it means is that in the meantime, so you're looking at very high redshift, like redshift order 1 or beyond galaxies through these type 1a supernovae, just like these Cepheids, which are standard candles, and you see that they are fainter than what their velocities would suggest. So what this means is that from that time to now, the universe has accelerated so as to make the distance between us and it larger. Right? It's sort of like if you observe a car traveling slowly now, but it's at a very far away distance, you would think that it has accelerated. That's why it could reach so far away by this time, something like that. Okay. Anyway, you'll learn the technical details. The thing to note is this is observed magnitude. This is redshift. These are data, type 1a data. And as you go to higher and higher redshift, you see the data points are this red line here at the bottom is a universe without dark energy. And you see the data points are, as you go to higher and higher redshift, are consistent with this sort of an acceleration that I was talking about. So we'll not go into the details of this. Okay, and this is I mean, you have seen this like at least 50 times, that if you measure the rotation curves of galaxies, and the farther you go, the rotation curves appear to become flat. So this is some external galaxy. You see the matter, just if you look at the visible matter, it only extends out till here, not much beyond. So if all the gravitating mass was emitting, you would have expected the rotation curve to fall like this, like a Keplerian rotation. But you observe it like this. So what it means is there's some sort of a invisible halo of matter which is dominating the mass of this galaxy, and that's giving rise to this. So this is one of the evidences for dark matter. There are multiple, independent evidences. It's not just this. The structure formation itself requires dark matter. CMB peaks require dark matter. So there are like multiple angles from which we sort of feel a need for dark matter. So that's why people take this very seriously. What about the baryonic matter? I told you about the stars and the ISM, but that's not it. There is a lot of normal baryonic, that 5% wedge. A lot of that is not accounted for in our own Milky Way if we don't count very diffuse gas, right? In fact, most of the baryons in the universe, I'm talking about baryons, normal matter, not dark matter. Most of the baryons in the universe are not in galaxies. They are in these things called, in this thing called the intergalactic medium. The gaseous streams which connect the galaxies contain most of the baryons in the universe, not the galaxies. And not only that, within a galaxy, for example, within our Milky Way, if you count the mass of all the stars, all the interstellar medium, and compare with the mass of the Milky Way halo, what you'll find is you can only account for 1/3 of the baryons. You expect the ratio of 5/30, right? 5% of that wedge, the pie chart, was normal matter. 30% was total matter, including dark matter. So you expect 1/6, but if you do this exercise, you only get 1/20th of baryons. So what it means, where are the baryons of Milky Way? And it turns out even within Milky Way, the baryons, there are a lot of baryons in this very diffuse atmosphere of Milky Way, and this is called the circumgalactic medium. Okay, so I mean, what this is trying to illustrate is we know certain things to within a factor of 2 or 10, but there are things which we don't really know much about, even in the baryonic part, and that's sort of is the circumgalactic medium, and it's expected to have 2/3 of the baryons associated with the Milky Way galaxy. So I will be talking about how do we measure the rotation curve of a galaxy like our own Milky Way, and how do we measure the movement of stars in the solar in the solar neighborhood. I already told you that the Milky Way is a spiral galaxy, and most of the gas and stars in the galaxy, in our galaxy, are going around in circular orbits. Okay, so let's see. So if this is the galactic center, this is the circular orbit of our sun. This is our sun, and let's say it's moving at velocity v0, tangential to its position. So this is the distance of the sun from the galactic center, and now we consider some sight line. So we are looking from the location of the sun to some sight line at a galactic latitude L, longitude L, and so let's actually consider an inner circle, say this one, and this is the inner circle that a star or gas inside the solar location takes. So this is the cloud that we are interested in. So the orbit of the stars and the gas is tangential, so it's perpendicular to, right, so this angle is 90 degrees, and let's say this angle is alpha. Okay, this is the tangent to this sight line, and so this is the alpha, this is 90 minus alpha, so this angle is also alpha. Okay, and the radius of this circle, the inner circle in this case, is say r. Okay, now we are interested in measuring two observables that we can actually get. The two observables are the line of sight velocity and proper motion. So this is the line of sight. How do we calculate the line of sight velocity? So we have to take, or the radial velocity. The line of sight velocity is also called the radial velocity. This is equal to the velocity of, so this we'll call v. This is the velocity of circular orbit at radius r. So the component of velocity along the line of sight is v cos alpha. So v cos alpha. And the component of this velocity along the line of sight is v0 sine L. So minus v0 sine L. L is the galactic longitude of the sun, as measured of this star that we are observing from the sun. So this is the radial velocity or the line of sight velocity. And let's so this t, I'm just sort of labeling this point as t, the tangent point. This point is the tangent point. And this is the location of our emitter. Let's call it, let's call this S. This is, let's just call it origin is O, and let's say position of the sun as P. So, so let's also call this distance from the sun to the emitting gas cloud or the star be distance d. Okay, so distance ps is d. So, and let's sort of put vector signs. So this is r0, this is d, and this is r vector, joining O and the position of the emitter. Okay, so so we can actually use the triangle POS and apply the sine law to it. We get POS. So so sine L by R is equal to, so we need this angle. This angle is nothing but so this is 90 minus alpha, and this is 90, so this is 90 plus alpha, pi by 2 plus alpha. So applying sine law, so this is sine of pi by 2 plus alpha, pi by 2 plus alpha, divided by the opposite side, which is r0. Okay, and sine of pi by 2 plus alpha is nothing but cos alpha by r0. So we can actually replace cos alpha here, and we get VR is equal to r0 by r. Sorry, this is cos alpha. So r0 by r sine L. So cos alpha is r0 by r sine L times b minus b0 sine L, and that's nothing but r0 sine L times v by r minus v0 by r0. And v by r for a circular orbit is nothing but rotation frequency omega, and v0 by r0 is omega naught, the rotation at the solar circle. So we have the radial velocity expressed as r0 sine L omega r minus omega r0 or omega naught. So one thing to notice immediately is that if the rotation of the stars or gas is solid body rotation, omega r and omega r0 are equal, and the radial velocity everywhere, measured everywhere, will be 0. Okay. Now, now how do we make progress? So what we are interested in is knowing the knowing about the rotation curve of the Milky Way, and also about the differential rotation, or the rotation, the state of stellar motion around the location of the sun. So what we can actually do is, so early on, people looked at in the solar neighborhood, because in the solar neighborhood you could measure distances to stars. So okay, so let's make this approximation that d, this distance d between the star and the sun, is much less than r0. In that case, we can actually Taylor expand omega r around r0. So omega r equals omega naught plus
d omega dr evaluated at the solar location times r minus r naught. Okay. Now, so how do we calculate r minus r naught in terms of d distance? So you can actually see this triangle. So you see r naught vector plus d vector is equal to r vector, right? So it's just this triangle POS. And what do we do is we write r, which is equal to r. This is equal to r naught plus d, and that can actually be approximated as r naught into 1 plus d dot r naught by r naught square. Okay, and what is d dot r naught? So remember, d is in this direction, r naught is in that direction. So d dot r naught is, so d dot r naught is d r naught, d times r naught times the cosine of angle between them, which is just cosine of pi minus L. This angle is pi minus L, and that's nothing but minus d r naught cos L. Okay, so r minus r naught is equal to d minus d cos L. So if your L is 0, then of course r minus r naught is just d. That sort of makes sense. Is minus d actually. R is smaller than r naught. So this is the formula. So we will plug this in here. This is equal to omega naught plus d omega dr. R minus r naught is minus d cosine of L. Okay, so what do we have for VR in the solar neighborhood, that is d much less than r, is equal to, so plugging that in here, what do we get? We get this minus that. What we get is minus r naught by 2 d omega dr evaluated at the solar location times d times sine 2L. Okay, and this is known as something. This is called this quantity here is called Oort's A parameter, and it characterizes the differential rotation at the location of the sun. Okay, so this is equal to A times d sine 2L. So if we assume circular orbits, the radial velocity should go like a constant times the distance times sine of 2L. Okay, good. And this parameter's value has actually been measured, and this is around 14.8 kilometer per second per kiloparsec. And so this is a rate. Okay, so the radial velocity is not the only thing that you can measure. You can also measure So you can, from the shift of lines, you can measure the radial velocity like this, but you can also measure something called proper motion for nearby stars. So what is meant by proper motion? Say, for example, this is the observer, and this is a star, nearby star, which is moving in some direction relative to the line of sight. Okay, so if it is not too far away, relative to the observer, if it is moving in this direction, and say this angle, this angle is right. So let's say this angle is alpha. So the velocity in the transverse direction to the observer is v sine alpha. Okay, so you will see the star moving relative to us in the sky, right? Because the transverse motion shows up as motion in angle. So if the star was moving towards us, perfectly towards us, then there would be no motion of the star in the sky because it's moving along the line of sight. So this movement of the star perpendicular, in the sky is called proper motion. Okay, and it's sort of measured in milli-arc second per year. So how much does a star, how much of an angle does a star move by in an interval of a year? Okay, so this is the definition of proper motion. So in addition to the radial velocity, we can actually also calculate proper motion. So, I mean, if the distance of the star is, say, distance d in this figure, and its velocity is v and this angle is alpha, so the proper motion would be v sine alpha divided by d, right? So this is the right. So this is basically the distance that it travels in the perpendicular direction, and d is this distance. So this is how much of an angle does it travel in the sky over some time t. Okay, and this theta over t is what the proper motion is, and that's v sine alpha by d. So the proper motion is higher, or the motion of the star in the sky is large, if either the velocity is large or if it is very near us, or d is small, in other words. Okay, so let's actually see. So we wrote an expression for the radial velocity. We will actually also write an expression for proper motion. Okay, so let's see. Let's look at proper motion. Oops. Let me actually have the figure here, and let me just write the expression first. Okay, what about proper motion? So this is the direction perpendicular to the line of sight. This is the direction perpendicular to the line of sight. Right. So what is the transverse velocity? V transverse is equal to the relative velocity in the transverse direction to the line of sight is v sine alpha minus v naught. So this is L, 90 minus L. So this will be L also. This angle will be L. So v naught cos L. So this is the transverse velocity that will help us get the proper motion. And again, we want to write sine alpha in terms of other quantities. So let's see. So if you look at PT, this side from distance from P to T, is equal to the sum of PS and ST, which is nothing but PS is D and ST is this is R. This is ST is R sine alpha. But PT is equal to PT is also equal to R times R naught times, so this triangle POS, POT actually is a right triangle. So R naught, this is 90, so this angle is 90 minus L. So is equal to R naught sine 90 minus L, that is R naught cos L. Okay, so PT is equal to both of these, so we can actually write sine alpha in terms of D and L. So sine alpha is equal to R naught cos L minus D by R, and we'll plug that in here. So this is equal to V by R into R naught cos L minus D minus V naught cos L. This is equal to, so let's see, so this is R naught cos L times V by R minus B naught by R naught. This is one thing, minus V by R times D. Again, we can use this approximation that we are looking in our neighborhood, so so we can actually use this quantity that right. So we can again use this expression for omega. So this is omega minus omega naught. Omega minus omega naught is equal to R naught cos L times d omega dr evaluated at the sun's position times minus d cos L minus omega times d. But we can actually replace V by R as omega naught d, because there is already a small parameter d here. So omega minus omega naught is proportional to d. So we are ignoring quadratic terms in d, so we can actually replace V by R by omega naught. Okay, so we have this expression. Let's see. Right, so this is equal to minus R naught d omega dr times d cos squared L is nothing but 1 minus cos 2L divided by 2. Okay, and then minus omega naught d. But we know we have encountered this combination already. This and this 2 absorbed in it along with it is nothing but A. So this is A times D, 1 minus twice cos 2L minus omega naught D. Okay, so let's see. So this is equal to So let's actually retain this. So minus r0 by 2 d omega dr. This is a times d times 1 minus twice cos 2l minus omega naught times d. Now, can we simplify it? So we want to actually combine this term and this term, this first term, which does not vary with longitude. So that's nothing but right. So that would be minus r0 by 2 d omega dr minus omega naught times distance d. So cos squared theta, so cos squared theta is equal to 1 minus cos 2 theta by 2. Is that not right? Yeah. Okay, I think this 2 will not be there. So I had made this mistake. This 2 is not there. So what do we have? We have plus AD cos 2L. Right? So because this minus r0 by 2 d omega dr is A. And then you have AD cos 2L. So this is actually a minus sign, not a plus sign. This is actually a minus sign. Let's see. This is what I get. Okay, now let's look at this. Can we sort of simplify this, combine this? So turns out we can actually write it as d by dr, this term, we can actually write it as d by dr of omega r squared, a half, with a negative sign, can we? And 2r naught, this evaluated at r naught, the solar position. So what do we get? Right, so we do get what's written up there. And this is another Oort parameter, which is called minus 1 by 2 r naught ddr omega r squared. Evaluated solar position is called Oort's V parameter. So Oort's A parameter was characterizing the differential rotation around the sun. Oort's B parameter is actually characterizing the vorticity around the sun. So this is proportional to del cross velocity or vorticity, or this omega r square is specific angular momentum per unit mass. I think this is 1 plus cos 2 theta. Sorry, my bad. This is a plus here. This is a plus here, and plus here. Okay, so what we obtain is the transverse velocity is equal to B times D plus part which varies with galactic longitude, which is AD times cos 2L. So this is the second quantity that we can measure for the stars in the solar neighborhood. In addition to the line of sight velocity we can. Now let's see how it looks like in terms of comparison with observations. So this is, for example, the measurement of transverse velocity divided by the distance, nothing but proper motion, measured in kilometer per second per kiloparsec, it's a schematic representation, and this is galactic longitude. Now, if you recall the expression, there was BD plus AD cos 2L. So there is this varying factor which goes like cosine of 2L, and then there is this offset which gives you a sense of B, right? The vorticity in the stellar rotation around the sun. So, and this is sort of a schematic representation of the data, and the data is noisy, and the assumption of circular orbits, perfectly circular orbits, is not correct, right? There are small motions around those circular motions which we have not accounted for, so that causes the scatter. The sun itself is moving relative to the mean motion of the stars in its neighborhood, and that the frame of reference of the stars around the neighborhood of the sun is called the local standard of rest, or LSR, local standard of rest. So this is about how we measure Oort's A and B parameters. So look at the proper motion as a function of longitude, look at the offset, that gives you the value B, and look at the amplitude of this cosine 2L modulation, that gives you the parameter A. And this was done by Oort in 1920s. But this is just local information. Can we know the rotation curve? In order to know the rotation curve of the galaxy Milky Way, we need to know the velocity at different radii r. How do we do that? Okay, so for that we need to look beyond the solar neighborhood, and in optical light, as I mentioned earlier, we cannot really see in the galactic plane because of dust obscuration. But fortunately, there is another probe available for the gas, which is the famous 21 centimeter hyperfine transition of neutral hydrogen, and or H1, and this neutral hydrogen is there in the galactic disk, and we can actually try to measure the line of sight velocity for this neutral hydrogen. We cannot really measure the proper motion for gas, right? Because these gas clouds are not so near us. Okay, so for applying these ideas to gas, we would be using this radial velocity value.
So now let's go to this. So you can apply this to anything where you can measure the line of sight velocity and proper motion. You can measure the line of sight velocity of gas, but you cannot measure like proper motion of gas, because there are no there are not so many gas clouds which are so nearby which can sort of move on the sky. But well, this is not. So if we so ultimately our aim is actually to get omega r, right? The rotation curves, or v as a function of r. So how do we do that? Right, combining A and B, we can get omega naught for the sun, but A and B are the local derivatives, but we want the full variation of rotation as a function of r, and for that what we need is let's see, so this expression so we measure this, we don't know this, we also don't know the distance. But we know that r is equal to r naught squared minus twice r naught d cross L plus d squared. So this is this distance. So basically, let's see, if you have a star whose distance you know, things are easy because you know d. But if you have gas, say 21, the problem with using stars in the Milky Way plane is what? Obstruction by dust. You cannot really see far. But this 21 centimeter line is actually a great thing because it does, you don't see any absorption there. It's in radial. Okay. And but the problem with that is you don't know the distance d. So how do you deal with it? So I mean the whole disk is full of H1 emitting gas, okay, and you're sort of seeing, say, in some direction. So all the H1 gas along this sight line will emit, and along a given L you'll see all of that with different velocities, right? With different line of sight velocities. Now this is how a map of line of sight velocity. LSR stands for local standard of rest. Local standard of rest means relative to the average velocity around the sun, a solar neighborhood. So this is contours of constant intensity of H1. This is longitude. This is positive. Right. So you have this. So for say you are at 30 degrees. You're looking at some angle 30 degrees. All the gas here along the sight line gives you emission. Okay. So at 30 degrees, if you see very bright patches here, large intensity, that means it's a gas, dense H1 emitting gas along some point. So it may be like a spiral arm that you're cutting at that place. So these features here correspond to spiral arms with higher gas density. The other thing to note here is that if you're we don't know R, so we can't really use this method in general. But if you go in this direction, the maximum line of sight velocity happens when the difference between this is maximum, right? This is fixed. When the omega R and omega naught differ the most, that's when you see a maximum line of sight velocity. And when does that happen? When the R differs the most, right? So the tangent point, is where the difference between this radius and R naught is the maximum, right? If you go farther than this, the radius from the center of this point again starts to become larger. So if you are at, say, 30 degrees, the maximum radial velocity corresponds to tangent point. So this so you can actually read off, and at the tangent point, we know this radius. This R is nothing but R naught sine L, right? For the tangent point, this is R naught sine L, and we know the radius corresponding to tangent point. So then for this particular point where VR is maximum, we know omega. We can use it and get omega at that radius. So we know R for the tangent point, and we know omega because everything else is measurable. In this expression, the problem is if you don't know the distance of a general cloud, you cannot apply this formula. But if you have measured the maximum velocity, that has to correspond to the tangent point, and for that you know R. And that's how you infer. Yes.
A peak in omega versus our rotation, the graph below.
This one is like the rotation curve.
You just take a
Yes. So what we are assuming is that this actually is very close. This peak happens actually very, very close, less than a kpc. So we just ignore that. So let's see. Now, if you take, say, this, this is the schematic of the sun. So this is the sun. Say you are looking at this L. This is the tangent point, right? And you're measuring all the light. So, so at that particular L, you have, in this particular position, you have actually crossed a spiral arm here also. So you will see it in the other diagram. In this diagram, the bright things are those dense features. And this actually is a code that I wrote, and these are essentially these sort of rings. So this is our sun. This is an inner circle. And how does so it has a maximum L. It does not go beyond this L. Right? This circle does not go beyond this L. So it's one of these guys. So if you look at R by R naught 0.5, its L only corresponds to this. This is just the radial velocity, and I've just sort of plotted this. And I'm assuming this sort of a rotation curve, which is sort of like starts from 0 and flattens to a constant value, extremely simple. So this is what I produced. So if you have a radius of R naught, R equals 10 R naught, this is what you expect. This is just that formula plotted, assuming this omega R, the rotation curve. So you see, at this particular L, you see these are the contributions from inner orbits, right? So these are the contributions from the inner orbits. These fully covering ones are the outer parts, okay? So now from that you can actually see that this is coming from the outer part of the outside of the sun's location, and these dense parts are the ones which are coming from the inner portions, and that's why they're like denser. These here, my angles are sort of opposite to here, so the x-axis is like inverted, but this is sort of the idea. Now this is, when you apply this to Milky Way type galaxy, this is the solar rotation 200 kilometer per second around the sun, and you can actually do this. So now you look at different L's, find the tangent points, you get omega at that particular radius, right? And then you just sort of bin it and plot it. So this is how it looks like. So you see it is not turned over till here. And this is sort of the north and the south. You can do it in this direction and in this direction. You can choose these L's or you can choose these L's, and you get sort of similar data. But outside R naught, you don't have a tangent point, right? So then applying this technique outside R naught, it's not possible because you don't know the distance. Inside, you could get the tangent point and so on. If you want to get the rotation curve outside, that's much harder. Then you have to know the distance to these clouds, H1 emitting gas. And that, either you use stars. Stars distance is easier to find than gas. You can also find the distance of the gas by sort of seeing absorption and stuff. So this is what you get if you apply this formula, but measure the D, the distance independently, and hence R independently.
So this R by R naught, the R is the tangent point, right?
That's correct. Yeah. So this R is really this. You get it from this. So this is about how you get the rotation curve for Milky Way. For external galaxies, it's not that hard because you are not inside it. Here, you're getting everything along the sight line, and it really is a mess. If you have an edge-on galaxy, you just go far away and you see the velocity. and that's distance. The distance we measure is the distance. Okay. So I think we'll end it here. Sorry about the mess. It was I had a different plan, but it's fine. So read about this rotation curves and how do you measure this. So we have covered this. You get a sense of how you get these lines, right? You know, I actually wrote this code to do it for myself. It's very easy. But what this allows you is to actually interpret these. These are called spider diagram, or something like that. I forget. So for a given L, you see all this gas, and at the maximum VLSR, it's the tangent point. Okay, so we'll start. In the next class, we'll start with gravitational lensing.